So, today we are just going to continue the design against temperature. So, you see this table, you can see here the yield strength reduction factor, which I think presented earlier also in terms of, if you go back to this, for 0.2% strain, you can see the reduction factor is 0.6 for 400 degrees. So, just a summary of the reduction factors for various temperatures for 0.2%. So, you can see here from 0.6 it goes down to 0.27 when the temperature reaches 600 degrees. So, how do we approach the design problem? So, basically we want to keep the stresses under control. So, if you look at this, the second column, the unity check ratio, I think most of you are familiar with unity check ratio. I think what we were looking at is the applied stress divided by allowable stress. So, applied stress does not depend on the temperature, it is basically the loads and the geometry. Allowable stress depends on the allowable stress factor, which is just percentage of yield, and yield strength itself is going to reduce by certain percentage, which you see from the column number 1. So, basically at 20 degrees, if there is no temperature change, then unity check is 1, is normal design. But when you have a 400 degrees increased, the yield strength reduced by 60%, and basically as long as you keep your applied stress levels at 60%, you correspondingly reduce your applied stress to 60%, then the unity check will remain same, because ultimately we want to maintain the unity check less than 1, so that the structure, the demand versus capacity is satisfied, structure does not show a failure case. So, that is the ultimate aim of the design. So, as long as you keep the temperature higher, keep the applied stresses lower. So, it is just a linear interpolation, I would say, or just a proportioning of the increased temperature, reduction in the steel yield stresses, and correspondingly you reduce the applied stress levels by reducing the load, or the alternatively you cannot reduce the load, because that is what your intended purpose of design. So, what we normally do is we increase the section capacity such that the applied stress levels are only brought to the level of 60% of the, that is for the 400 degrees, just a typical example. So, if you want to have any other factor, so just proportionate the reduction in yield is equal to reduction in the applied stress level. So, just a crude way of doing it. If you understand this, I think then it is very easy. Basically what we are trying to maintain is the unity checks to be maintained as if the original unity check when the stress levels are maintained at 20 degrees, just normal the operating conditions. So, that is what is demonstrated in this particular table, because most of the design methods for temperature it is going to be this way, except in some specialized cases we may go beyond the yield. So, if you look at this diagram, one important thing what we have just now discussed without realizing the changes happening to the stress strain curve, we simply reduce the stress levels to the same as the reduction in the yield, which is not very good, because we do not look at the stress strain curve, because the slope of the stress strain curve is very important, how the behavior is. You see this curve is the solid line, this solid line is the change of the stress corresponding to strain at various points along the increasing strain levels. So, basically from, if you look at this first point is about 0.2% and then 0.4% and so on, it keep on increasing up to say 1.8% or 1.7%. Now, you see it is continuously changing, it does not follow a typical linear elastic and then perfectly plastic, it is just basically a continuous nonlinear profile. Now, we need a modulus of elasticity value for design purposes. Basically when you do a analysis, you need stiffness, for calculating stiffness you need surely the modulus of elasticity value. So, which value we will take? If you have a very nice typical linear elastic one line bilinear stress strain diagram, then it is very easy, because you will take the initial slope, because most of your design is going to be within the 0.2%. You see here it is of course this first one is 0.2, but even before there was a slight kink there, even maybe 0.5% there. So, it is continuously changing, and basically we need to find out what will be the best assumption or approximation we can make, as we discussed about yesterday. We can take a initial modulus an average between this point, which is 0.06 and basically 0.2, and pass through a dotted line, which takes us to a typically strength reduction factor of 0.6 basically here, and this, and make a bilinear graph and take that as your yield strength, 60% of the yield, and corresponding to a strain value of 0.2 or slightly higher. So, you take that slope as the modulus of elasticity used in your analysis. That is the first approximation. So, we take 0.2% as the approximation to find out what is the approximate modulus of elasticity value. The second approximation could be potentially using the same 0.6 or the corresponding yield value, just take a straight line joining origin and the point of intersection with the 60% reduction, and you will see a reduced modulus of elasticity because the slope is reducing. So, you can see here there is substantial difference when you use a modulus of elasticity using the first option B. You will see that the stiffness is more compared to the second one, stiffness will be less. Now, how do you approximate depends on the person who is doing the work. Now, basically this is where the principle needs to be applied. You have to be conservative, but not non-conservative. So, if you use the choice 1 or the option B, they call it choice B, it is not good because you are taking higher stiffness in your system analysis compared to the second one, and most of the time both of them are not correct, because if you are having a value of your stresses at this part, maybe that point is correct, but what about in between? In between you have a continuously changing values of the ratio of stress and strain, and if you take only one value as a representative, because you are doing a linear static analysis, because you are trying to do a simplified structural analysis, that is why you are doing this. But what if you do a non-linear analysis, then you do not need to assume like this. Every time you can divide the whole graph into say 10 sub segments, every time you can take the different values of modulus value whenever the strains are increasing. So, for lower strain you will take the values somewhere here, as the strain value is increasing, as you have a large deformation problem, then you can continuously change the tangent modulus, which easy to calculate from this graph. So, that is where the necessity of the second order or so called non-linear analysis of structures is required whenever the strain values are larger than 0.2% and then higher. So, whenever you have a material characteristics not bilinear, I will show you one of the bilinear graph. I think we have seen it before also, straight line and then just a perfectly plastic, and that type of problem you do not need to worry, whereas here you see here multi segments of linear proposition here and continuously changing from starting itself, which will be a typical behavior for steel under increased temperature. I think that is what we saw also yesterday, that several graphs in one particular picture for steel at 20 degrees, 400 degrees, 500 degrees, you will see that there is no more a bilinear graph. So, that is one thing very important that you need to remember. It is not only the yield strength reduces, but also two things happen. There is a reduction in the modulus, and also the modulus is not a constant value throughout the range of deformation, it is going to be changing, which needs to be accounted for if you are using higher strain value. If you are using 0.2% strain, I think you no need to worry, because anyway the difference between this and this probably a very small difference, but you decide to go for a large deformation because you want to absorb more energy, you want to allow more strain. More strain means you will go somewhere here, then the strain values needs to be appropriately taken to calculate the modulus of elasticity. That is where the difference, and it all depends on the choice of analysis method. If you still use the conventional allowable stress method, none of this what we discuss here can be incorporated, because the method itself uses only a single Young's modulus value, which either you will use the initial or you will use the final. So, it depends which method. So, if you go to a nonlinear second order analysis, then all these things can be incorporated appropriately, and that is why when you are designing a basically critical components in the system, for example thermal nuclear reactor, you do not do a simple static analysis like what we are trying to do. You have to do a nonlinear analysis to simulate the temperature behavior of the structure and make sure that all the possible the responses are taken into account. Whereas, when we are designing a simple structures like the protective barrier, you try to go conservatively and try to do a static design as long as you pick up the right values. A typical elongation of a beam not restrained in any direction. So, now when the temperature increases from T naught to T, you see the delta T happening, and basically you can find out the thermal strain in any direction as long as it is not restrained. So, it is just going to expand this way, expand longitudinally and in the transverse direction. So, you could easily calculate, but what happens if you just try to restrain in one direction along the end. Say you have put one restraint on this and restraint on this, that the beam is trying to expand in any direction wherever the degree of freedom is free, and that is what will happen when you try to do look at a beam. You just hold it on both ends and it is trying to unable to go in the axial direction and also unable to rotate at the end, because you might have fixed. But if you have allowed to rotate, and that is what will happen, when you allow the ends to rotate because simply supported boundary conditions and just trying to. So, you can see here one important thing is when the beam is bending, one of the surface is going to get a compressive force, the other surface is going to get the tensile force. So, this shrinkage is also a problem depending on type of cross section. If the shrinkage is too large, buckling may initiate, and that is where most of the failures due to fire happens because of this large deformation, unable to take, and then suddenly, though there is no axial load, the problem is because of the shrinkage length of the member, unable to go further down, just try to buckle locally and fail. So, that is many of the cases the failure due to fire is because of this phenomena called shrinkage length. There are several methods described by API for the design. So, what we have looked at is the critical parameter is the reduction factor, modulus of elasticity reduction corresponding to the temperature, and in here we got about typically the first two methods are same, almost same I would say, except there is a little difference in accommodating the temperature. The first one is very simple, keep the temperature below 400 degrees, means is as long as you have the temperature below 400 degrees, you do not need to do any design as long as you keep the unity check ratio corresponding to the yield strength reduction. So, basically that is the table that is going to be used. The linear elastic limit, as we normally do most of the design in the last several years, is basically just replace the yield strength by the actual reduction factor. So, if you have 0.6 Fy, you replace throughout and replace the modulus of elasticity corresponding to either the tangent or the initial modulus, and this is what practiced by almost all designers in the industry for so many years, because it is quite easy, just replace modulus value, replace but only one important thing is the linearization has to be done properly, like we saw one different choice B, choice A. So, if you do a linearization conservatively, taking a lower side of the modulus properly, not a problem, but if you take the choice A, if you take choice B, higher modulus value, not very good. So, that is the only difference. The elastic and elastoplastic method is typically a second order analysis, both material and geometry, because it is a large deformation problem and material itself is continuously changing, and which normally not done except for very specific cases, and probably what we are looking at is the ultimate capacity, not the elastic capacity. So, ultimate capacity at any time the structure does not collapse. So, under high temperature, so some of the members may fail, but still the system does not collapse because you have redundancy in the system. So, that is what we are trying to prove in the third one, and typically it is not done for conventional design, special cases, even for jackets we do it, but not for fire, but for ship impact. But some cases people have attempted to do a fire simulation, if you lose one of the leg, whether the system can still be stable, because during fire you could get such a situation there where one side of the leg is damaged or collapsed. So, such analysis is basically taking into account the plastic capacity available. That means beyond yield, you might have seen we have been using a triangular stress distribution for elastic, When you go to plastic, you have a rectangular stress distribution. So, the distribution across the section and distribution along the length. So, those will be taken into account in this, whereas the first two methods nothing of that sort, simply a triangular distribution and basically conventional allowable stress design. So, let us look at quickly what the zone method. API has given you a figure you see on the right hand side comprising of all three methods. The dark color at the bottom you can see 20 degrees, this is 20 degrees, the design as per operational temperature with no temperature increase. So, you could see here I have just defined the zone method restricting the temperature to 400 degrees. So, as long as you have the temperature below 400 degrees, the unity check will be 1, and as long as at 20 degrees you design the system in such a way that the unity check is 0.6, yeah. So, basically that means the applied stresses are kept low at 20 degrees and at 400 degrees the unity check will become 1. So, very simple, just proportioning, you know, basically that is the idea behind the zone method, but only the difference is we are keeping the temperature below 400 degrees, and that is the most projects applied this principle, because temperature higher than 400 degrees, you know, the reduction factor is so large that the section size has become too big. So, we will look at alternatives how to bring the temperature below 400 degrees, rather than do not provide any protection, but just allow the temperature to grow as big as. In some cases what we normally do is have insulation in many part of the structure, you know, basically the thermal coating, or if the design is because of not accident, because I think you might have seen a structure called a flare structure, we were trying to fire the excess gas. I think one of the days I have explained you there will be a structure to fire the gas that is coming out of oil platform. I think first few classes we were discussing, if there is a purely oil platform designed for oil production, but there will be a gas coming together with the oil, the quantity is so small that you do not want to do production. So, such times you actually fire the gas instead of sending it back to land. If it is a predominantly gas platform, and then you produce, because you got to change the equipments. So, in such type of cases you will see, I think probably I will show you a photograph, the firing of gas will actually affect the structures in the vicinity, is not it. So, that type of design you can provide a barrier, you actually make a barrier or make the structure so long that the temperature reaching the main structure is within 400 degrees, just a planned activity. So, it is not an accident, it is actually a operational case, but we can restrict. So, most of the time such type of cases we will be assured that the temperature is below 400 and then just come up with a. So, 20 degrees the unity check is basically 0.6, and we know very well that 400 degrees the yield strength reduction also is 0.6. Only one thing is we forgotten about the modulus of elasticity, because we are looking at the, if you look at 400 degrees, just let us go back quickly what happens to 400 degrees somewhere here, 500, 400 is 1, 2, 3, I think this is the one, 200, 300, 400. So, if you look at the 400 degrees, still it is not linear. If you look at the 20 degrees, is just one straight line and a horizontal plastic line. So, basically still there will be considerable change in the modulus of elasticity depending on what reduction factor. For example, for 60% you may be taking somewhere here about 200 something. So, if you join this line and this line, you will see a at least 20 to 30% reduction, 20% reduction in the modulus of elasticity value, which is what we are ignoring in the zone method. So, you got to be little bit careful. As long as your temperature is say 200 degrees, probably not bad, because the yield strength reduction from 350 up to probably 300, and the slope between this line and this line is very small change. So, that is where you have to be little bit careful. So, the idea behind the zone method is simply designing the structures with the reduced applied stress corresponding to the yield strength reduction factors for 400 degrees, and that is just a typical example. I have given you applied stress is 0.6, Fy, and basically at 20 degrees, and we know very well that the allowable stress or the safety factor in allowable stress design is 1.67 taking 0.6, and gamma is also a increase factor, which is normally, if you remember when you design structures for seismic condition, we normally increase the stresses to 70%. I think most of the codes are describing, I think whether it is API or IS 1893, during a seismic condition you can increase the stresses to 70%. So, similarly you see here the stress increase factor of 1.67. When you substitute all of them, you will get a unity check ratio of 1. So, that is the idea behind, you keep the stresses below certain level, the unity check will be, only one thing is the modulus value is not changed and just completely ignored. As long as the change is smaller, then the system behavior will be same. Now, if you go to the same zone method at higher strain values, what we discussed is just now only 0.2%, which is okay as long as your deformations are smaller. But what happens when the strain values you want to allow larger, because you want to have more deformation, and in such cases the allowable temperature, for example, when you restricted the strain to 0.2%, 400 degrees, your unity check value is 1, whereas when you allow larger deformation, the strain values are higher, then you can possibly allow higher temperature. So, that is another thing. So, the higher the deformation values you would like to allow, you can have the slightly increased temperature, like for example, if you want to allow 2% strain, then you can go for higher temperature, because it is going to. So, basically what we try to important note is the note at the bottom, the modulus value has to be appropriately taken. So, if you are not taking, then it will be incorrect system analysis, though the components are designed correctly, but the behavior of the system will not be correct. The second one is the linear elastic method, but exactly the same, only thing is the system analysis will be taken into account the average modulus of elasticity, and we do allow temperatures beyond 400 degrees. So, you can see here this is a 400 degree line, 450, 500, 550 and 600, all of them are drawn in the same graph. So, the typical example, it will be exactly the same design, only that we have, for example, unity check value of 1 at 600 degrees, basically your applied stress must be reduced to 27%. So, when it was 400 degrees, we could actually allow up to 60% of the original load, whereas when you go to 600 degree C, and we can only allow 27%. So, basically that is the idea behind you keep increasing the stress, you have to keep reducing the applied load, and otherwise you can't maintain the unity check of 1, which demarcates the failure to non-failure. So, that is the simple difference. Both methods, if you consider basically the change in modulus of elasticity, both methods are reasonably correct as long as the strain values are smaller. When the strain values goes larger and larger, that is where the problem starts to crop up, because the modulus values will start changing. The elastoplastic method, commonly used for large deformation structures, not for stiffened steel structures, basically specialized structures, like you can use this method, because it is a time consuming process. You have to model the material characteristics, you have to model the geometric second order nonlinearity, and whenever you go beyond, then you will be using the extra strength, the reserve strength available between the elastic limit to the failure, so also called ultimate strength, which normally in most of the design we do not allow, and you will use that with the appropriate factor of safety. So, basically in summary, the design of structures for steel is a very simple idea. What we need to know is the strain value, increased temperature multiplied by the thermal coefficient, and you will get the strain. From strain you can go back to deformation and stresses, and correspondingly work out the unity check ratio, or you limit the temperature to a particular limit and then calculate the reduction factor in the yield, compute what will be the allowable applied load, or you calculate backwards what will be the section property required, either way. So, basically what we need to remember in design for temperature is is trying to modify the yield strength and the Young's modulus. So, in the examination point of view, I think you will be given a simple exercise of reading the chart, nothing more than that, because basically system analysis cannot be performed, because there you are replacing the Young's modulus value, whereas in the component calculation either you will be calculating the section property required, or you can calculate the limiting temperature or limiting strain. So, most of the time you will use this chart what we were looking at. The next one what we are going to see here today is the design against blast. I think we have discussed about this fact that blast initiated fire or fire initiated blast are have to be treated little bit carefully. So, in this case we are just going to look at the fire initiated blast. Fire is already occurring and there is a blast, and that blast, the behavior needs to be understood. The load is going to be dynamic. I think most of you might have studied dynamics of offset structures going through a course now, no? Not yet. The single degree of freedom response, at least you need to remember. I think you might have also studied in your basics, in your physics. So, basically we need to see how the response, if the loading cycles or the loading frequency is comparably close to the system frequency, then how the response is going to be increased. We call it resonance. I think that is the most critical part of this whole business, both in terms of cyclic loading like wave loads, or in this particular case the blast is going to be a pulse load, very small duration but large amplitude. So, what really happens, basically you will be locking into a resonance area where the amplitude of response of the structure could be several fold higher than conventional static response. If you calculate a simple beam, apply the blast load and try to find out what is the deflection at the center, you may get few millimeter if you just ignore the frequency response function, or if you take into account you may get several times, maybe 5 times, 6 times. So, that is exactly we need to find out. The blast load is going to be dynamic, it is not a static load, and the duration, the smaller the duration we are going to have trouble. Imagine you have a blast and just over a long period of time the behavior will become almost equal to static loading. That is exactly the idea, and we will see how the behavior can be modeled. Now, if you look at this typical compartment, blast occurs as long as the ventilation is there. The most important problem is the ventilation. If you do not have ventilation, what is a blast? Blast is basically an ignition of a source material. It could be gas in this case of platform, or it could be an oil, or it could be other types of sources which normally we do not use in offshore platforms. So, basically in this case, if the ignition point is congested in that area, you got a lot of obstructions, there is the possibility of the exploded gas is unable to escape, then there will be a further increase of pressure, which we call it the blast over pressure. So, you make a compartment and just explode, and typically that is what will happen, and that is where if you have large ventilation, the gases could actually, the gas cloud can escape, so that the pressure, the over pressure will be reduced. In fact, several times the damages are very large because of this, the ventilation is not there. That is why when you explode something in an open space, nothing really happens, but when you explode the same thing in a congested space with several debris and other materials in the vicinity, could do a serious damage. So, that is why the blast, basically the combustion of unburnt gases trying to escape, whatever is burnt is okay, it will become a smoke, but the unburnt gases trying to escape will build up pressure and trying to expand, and that is called the over pressure generated by the blast. And that is why when you design an offshore platform, you need to make sure that all directions, whenever there is a large equipment, you need to provide large space around and also ventilation to make the gases escape, both during the blast as well as during normal operation. So, you see here in this picture, as long as the obstruction or no obstruction, if there is an obstruction, if it is uniform, then the net load is 0, or if there is no obstruction, everywhere it can actually expand nicely. So, the net load will be simply not there. Whereas, there is a unequal obstruction or a kind of distribution something like this, then there will be a net load because of the differential pressure which is caused by the drag. So, that is exactly the idea happening in the real scenario where the equipments and the other facilities around a particular location of ignition and explosion is not definitely going to be uniform. There is no point of doing that. So, that is why that net load causes damage to structures in terms of trying to rip off the structure in the local vicinity, or that whole thing can go and impinge onto a neighboring wall or a bigger obstruction. Typical basically the overpressures expected in the offshore platforms, not as high as 7 bar. Most of the offshore platforms are designed for less than 1 bar, many, but in special cases some of the platforms also designed for 3 bar overpressure. So, you could see here 3 bar is nothing but 300 kilopascal, which is 30 ton per meter square. So, if you look at 0.2 bar is 2 tons per square meter. So, imagine 2 ton per square meter is a very large loading, 20 kPa is a huge loading, and when you design for 30 ton per square meter, which is possibly the heaviest load, the civil engineers may not have even seen such type of loading, could possibly not possible to design any structure for such type of loading, especially when you want to design for gravity. So, that is where the problem will come. So, you can see here the expected type of damages to human being, because after all we are worried about the injuries and the mortality. So, basically if you have such type of overpressure, and that is where the damage is too much. So, most of the cases we have less than 1 bar, sometimes as much as 7 bar, only very few platforms, especially when you have a congested space. So, how the blast wave interact with the structures depends on the type of obstruction and basically the enclosure that you have. So, you see here the similar to our the shock waves, you have the surface waves when you go to our wave basin, the incident waves and the reflected waves get actually interacting, and the effect will be increasing furthermore. So, you can see here an obstruction is here, and basically the shock wave propagating from one end because of the explosion comes backwards from an obstructed space or a wall. So, you will see that unless you have 100% ventilation, you will see a severe interaction, which will be very difficult to simulate, and that is where the pressure will build up, and wherever the weakest component on the wall will try to explode in that direction. So, this idea is the prediction of blast over pressure. Typically there is no software to simulate this. What people have done is they have done several full scale testing. The joint industry report which I was referring, the interim report, basically have done several full scale model fabrication and then ignited with artificial detonator and measured the overpressures with several degrees of ventilation. Have, for example, in this particular case you enclose it and only provide a weaker particular space, so that exceeding the particular overpressure, that will actually blow off. So, that means the overpressure build up is so much. So, like that they have done the experiments and come up with that report depending on the porosity of the structure. Porosity does not mean that we make the structure porous, the obstructions on the facility. You have pipes, you have equipments, you may have structural columns, you may have structural beams. So, put together a volume is defined, x, y, z volume, and how much is occupied by the obstruction, how much is not occupied by or empty space. So, that ratio is very much important. Depending on that, the values are recommended, and basically we will see in the next few slides. So, the blast over pressure is very important to obtain from references or from other sources, so that it can be used for design. Typically you see here, as long as you know the velocity of flow, theoretically you can simulate gas flow around solid bodies or obstructions. you can calculate the drag force as long as you know the velocity of the flow. So, depending on the type of object that is being, if it is too small, mostly the flow will go around creating a drag, and if it is slightly bigger, not too big, it may actually create a shock force, because it is an obstruction that is causing. Depending on the shape and size, things could be different, but as long as you know the velocity, you could use the projected area to find out what could be the potential drag force that causes. So, the potential drag force, once you know, then you can design the structures. Typical pressure time curve is just given in this graph. So, you can see here potentially it will be less than 150 millisecond, very small, time period is quite small. The most important is the rise time, which is basically, so you see just idealized, just like a triangle, whereas you may not see a nice triangle like this, you may see things like this changing within the time period, but for the analysis purpose we normally use a simplified triangle. So, the three parameters, one is the peak pressure, basically the value of the peak, it could be at the center or it could be at the off the center, because not necessary that you will get a nice symmetric triangle like this. And then the rise time in this case is 50%, just basically half of the total time, and the total duration of the pulse. So, these three parameters are required, so that we can go back to a mathematical model and use the dynamic equation and substitute the loading and can find out the structure response. And as I mentioned earlier, the peak pressures vary from 0.1 bar to 10 bar, typically for offshore applications not more than 2 or 3 bars. And depending on the type of impulse, you can go to the last one first, the ratio of the total duration divided by the natural frequency. If it is greater than 2, that means basically behaves as almost close to static or quasi static. So, you do not need to worry about so the duration of loading is very large, is sustained loading, is not it. So, you can treat it as a static structure, you do not need to worry about dynamics. Whenever the pulse is so small, then it is just excited and then the load reduces. So, the structure starts vibrating, depending on the frequency you will see into resonance, and that is the most important one. And you can see here the rise time is quite very small or does not exist, straight away value picks to a higher value and starts reducing, and most of the detonated explosions will be something like this. The peak value will be reaching in very small period, almost 0, and then comes down, whereas when the explosion happens after a fire, you may see that there could be a similar situation, because already fire is there, the detonation can happen very quickly. So, these three we need to understand how we deal with it, because each of this area you can define a particular analysis method. So, as I mentioned, the last one we really do not need to worry about dynamics. The first one for sure very short impulse, and the second one is in between 0.4 and 2. So, basically for the first and the second one we use a dynamic analysis, whereas the last one we could use the simple static analysis, of course with a slight increase in the dynamic load factor, an approximation which we could use it, because still we are trying to convert the dynamic loading to a static loading. So, we just multiply by a dynamic load factor, which is what is mostly practiced in the industry, because the first two involves considerable amount of time and effort. So, what we try to do is we try to do a single degree of freedom model of the first 2 items and try to find out what could be the possible dynamic load factor, go and apply to a quasi static model, which is a simple static analysis, and increase the loading by that amount and then find out what is the response. So, structural resistance against blast loads, basically the idea behind is a large deformation, and you can see here the important thing is when the large deformation is occurring, should not go and impinge onto neighboring equipments, because that may trigger subsequent basically blast or fire. So, the important parameter is, one is the over pressure, which we discussed about it, basically for large obstruction because is unable to escape, or smaller obstruction you may actually have a drag force which is very similar to any drag component like wind. Acceptance criteria, we just need to fix up, one is the strength limit, the other one is the deformation limit. I think deformation limit is very easy to understand. We want to limit the deflection to say half a meter, because we want to keep the equipments in the near vicinity, or you may set a value to 2 meter as long as you want to waste 2 meter space in that vicinity. So, it all depends on the space availability. As you know very well, space availability is very difficult in offshore platform, not easy to get a large open space. So, you typically give a meter and put all your equipments around. So, when the deflection happens, so the deformation limit is very easy to set. How you obtain the deformation is the most important, whether you want to do a simple static analysis or you want to do a second order nonlinear deformation, or you do a quasi static analysis with a load factor multiplied. Strength limit, again similar idea like what we discussed about the temperature. Similar, you can do a static analysis multiply by the dynamic amplification, or you can do a nonlinear analysis.